we're going to use this powers chart to help us solve exponential questions. And exponential questions are where the x is in the exponent. And I don't know if you started to notice that after you got introduced to algebra, which was x's, you started solving equations. So in middle school and in grade 9, you'd solve equations like x plus 3 equals 5. And you like move the 3 over and get x is equal to 2. Then we started to get the x into different things to make it more complicated. You had x squared equations where you had to square root both sides. You had x squared equations with another x where you had to factor. And so we've been developing strategies for solving for x in a bunch of different places. We put x inside of sine, cosine, tan, and you learned how to solve for x with trigonometry. In our unit that we just finished, we now can factor x cubed, x4, x to the 5. And you can solve by factoring even bigger ones with synthetic division. But one of the places that you have never solved for x yet is if the x is in an exponent. And we need a whole new branch of mathematics for this. Later on, we're going to learn about a logarithm. That's the whole new branch of mathematics to solve for x in the exponents. But sometimes you can solve for x in the exponents just by using this powers chart that we wrote at the beginning. And the idea looks like this. If you had something really, really easy, like 3 to the x equals 3 to the 7, do you think you could solve for x? What do you think x is?
7.
7. It's pretty obvious, just by observation, the x would have to be 7 because on the other side where the x is, I have a 7. So if things look like this, the same base on both sides, one power on one side, one power on the other side, does it make sense that those exponents would have to be the same? So that's where we're going to use our powers chart. Our goal is this. Can I write both sides with the same base and as a power? And I'm going to use all of my exponent rules and my powers chart to do that. And the way that it's going to work, like in A here, I have 4 to the x and 1 over 256. And I'm going to go back to my powers chart and say, do the numbers 4 and 256 ever happen in the same columns? And actually this one happens in the same column twice. Do you see that 4 and 256 happened to be powers of 2? And 4 and 256 also happen to be powers of 4. Because 4 is 4 to the 1, and 256 is 4 to the power of 4. So what we can do in this question is we can first say, well, I know that 256 is 4 to the power of 4. And if I can get both sides to have the same base, then I could just look at the exponents. But right now this 4 is on the bottom. Do we know how to move that 4 to the top? We're going to use our negative exponent law. And once we get to this part, I wonder what x could possibly be. I often write, so x has to equal minus 4. And I write the so part because we're actually just using observation. We haven't solved for x mathematically by getting x by itself. That's normally what we do when we solve for x, right? We do mathematical manipulations to get x by itself. In this case, we just answered it by observation. So that's why I write that little so there. Okay? 27 and 9. Look on your powers chart. Are those ever in the same column? Yes. 27 and 9 are both powers of 3. So what I'm going to do in the question is I'm first going to change 27 to 3 cubed. It was to the x, so it'd still be an x there. I'm going to change 9 to 3 squared. It was to the exponent 2x minus 1, so it's still to the exponent 2x minus 1. And we want to get a single power on both sides, so we can say the exponents have to be equal. Do you remember your exponent law for power to a power? Add, multiply, subtract, divide, guess. What was the law? Multiply, yes. So here 3 times x will be 3x. Here, 2 times 2x minus 1, you'd have to distribute, be 4x minus 2. Does it make sense that what's in the green circles then would have to be the same? If you get the same base on both sides and you have a power on both sides, and one power 3 to something equals another power 3 to something, the somethings, which is circled in green, have to be the same. So I'm going to write, so the 3x has to equal the 4x minus 2. Could you get x by itself now? I can move x's to this side, move my 2 to this side. Sure enough, x would have to be 2. This is our non-calculator way of solving for exponents. If you can get the bases the same using your powers chart, then the exponents would have to be the same. And then if the exponents have to be the same and you make them equal to each other, you can solve for x. We're going to get into problems later on because we're going to get questions like this. What's the problem here? 17 isn't on our powers chart. 16 is, right? 16 would be 2 to the 4. In fact, if I had to estimate this, I'd guess 4.1. Ooh. I'm going to see. Was I close or was I off? So I go to my calculator. I guessed 4.1. 2 to the 4.1. Oh, too much, but I was close. Oh, maybe it's 2 to the 4.08. Oh, too late. Oh, 4.09. Oh, a little bit too much. Can you see I could do this? I might get stuck doing this for like a very 8. Oh, too much. It's addicting. He's like, I want to get closer. Ooh. 0.0875. Oh, I keep getting closer and closer and closer and closer, right? And this is exciting math work, right? Getting closer and closer and closer. We're going to want to figure out how to do this, and eventually we're going to do stuff with logarithms. Oh, it was supposed to be 4.087462841.
You were close.
I was getting really close. Look, I was already at the... Oh. Another 5 minutes I would have been there. For sure. So we're going to get to questions that we need a calculator. And you saw me hit the log button. We're going to have to figure out how the log button works on our calculator, what it means, and how we can use it to solve these equations. But right now, we're all about our powers chart and doing these without our calculator. So questions you can circle from number 1 are 3, 4, 5, and 6.